Hello, everyone. Welcome to the introduction to our labs for the week of November 2nd. This is Jeff Wilkerson, Professor of Physics at Luther College, for those of you who might be watching who aren't part of the course. And this week we're going to do exercises 28 and 29 out of Contemporary Activities in Astronomy by Hoff and Wilkerson. Exercise 28 is about galactic clusters and HR diagrams, and sometimes we'll call galactic clusters open star clusters. So these are clusters of stars, and clusters of stars are wonderful laboratories for us to use to understand stellar evolution, and that's what we're going to do a little bit here this week. We'll be talking about it in class, and we'll be working on it in lab, and it'll run in early next week as well. But the reason open star clusters, globular star clusters as well. Globular star clusters are a different class of star clusters. We won't talk about those here right now. We'll talk about those later this week in class. But what we're going to look at these open star clusters. These open star clusters live in the plane of our galaxy. So the Milky Way is a disk with a bulge in the center, and in the flattened disk is where these open star clusters live. So if you look at a side view of the Milky Way, very roughly, it looks something like this. A little more symmetric than that, but anyway, we live here in the plane of the galaxy, and open star clusters are in the plane of the galaxy as well, dotted all along here. The next exercise we're going to talk about, exercise 29, looks at this in great detail. So we won't talk about this here right now. But we see these open star clusters, and the thing about the disks of spiral galaxies that we want to talk about here as we get into the later stages of the course is that the disks of spiral galaxies are stellar factories. New stars are being formed. Stars. So these are stellar neighborhoods. This is where stars are formed. They live their lives, and then they reach their end states, whatever that's going to be. And we'll talk about all of these different paths here in the next couple of weeks. And so the open star clusters are where this is happening. Since star formation is occurring in the disks of spiral galaxies on an ongoing basis, because there's free dust and gas there that can collapse to form new stars, open star clusters, or galactic star clusters, as your lab book calls them, can be any age. And so they can be all sorts of different ages. But for us, the key here of what we're trying to do is that the stars that are in a cluster were all formed at the same time out of the same cloud of gas. So something happened, probably a shock wave from a supernova explosion came by and collapsed that cloud of gas. Right? The cloud of gas was probably sitting there happily in hydrostatic equilibrium with gravitational pressure pulling inward, gas pressure pushing outward, and those two things equaling each other, and the cloud of gas just sits there. A shock wave comes by, hits that cloud of gas and compresses it, and it starts gravitational collapse, and instead of forming one big star, it forms lots of individual smaller stars. And so these open star clusters can have tens of stars to hundreds of stars to thousands of stars in them, unlike globular clusters, which are hundreds of thousands to a million stars in them. This is what we see in these open star clusters. So these open star clusters are all sorts of different ages, and we're going to look at that today. And so we're going to look at a few different things. What that tells us, if they were all formed out of the same cloud of gas, all these stars, when they formed, should have had pretty similar chemical composition. And if they were all formed out of the same cloud of gas with that shock wave going by, all these stars in a given cluster, any star in a single given cluster, should have the same age. So if we see a difference between star A and star B, that difference doesn't come from initial chemical composition, and that difference doesn't come from age. If you look at any two stars out in the field, out in the rest of the galaxy, you look at them, any of those two stars, you don't know when they were formed, you don't know where they are, you don't know what their sort of initial chemical composition was necessarily. So you have to take all of those differences, you have to consider all of those differences to be part of what makes these two stars look different. That's not the case in a star cluster. And that's the other factor of a star cluster. All of the stars are basically the same distance from us. Sure, the cluster has a little bit of extent, but the galaxy is huge. And so that little tiny extent we can't tell at all. So a given star cluster, every star is the same distance from us. Remember the way we've worked to compare absolute magnitude to apparent magnitude. stars look fainter if they're further away. We don't have to worry about that in a star cluster. If a star looks fainter, it is intrinsically less luminous. So that's a great thing about a star cluster that helps us do this work, is that to understand the stars are all the same distance from us. So brighter means brighter. Brighter means more luminous intrinsically, and the same chemical composition and the same age. And so all of these stars, anything that causes the stars to look different must be due to something else. And so this is what we'll be talking about in class a lot here in the next few days. Is what drives that, and what drives it is mass. We can say that initial stellar mass is the primary driver of stellar evolution, and we're going to work on that here. But for the lab today, by looking at the HR diagrams of galactic or open star clusters, we can deduce a few things. And one of the three things that we're really going to be working with in our lab here today, one is we're going to get the something called we're going to get the age of the cluster, and we're going to get the distance to the cluster, and we're going to get something called the reddening of the cluster, or the color excess. We're going to measure the color excess to tell how much the stars have gotten reddened. And remember, we've talked about this a little bit in class. Remember that the stars look redder the further away they are, often because of more dust they have to come through. So they have more and more dust they have to come through, and the red light gets scattered out. The blue light gets scattered out preferentially to the red light, and more red light gets through relative to the blue light, and the stars look redder. So this is going to form the heart. Once we do this work here today, this is going to form the heart of Project 3 that we're going to work on next week. And so this will be part of that project, as well as interstellar reddening. So we're going to measure that for 9 different open star clusters. So in your lab book, you've got the HR diagrams like this of 9 different open star clusters. Let's use this one over here, one that I haven't written in quite so much. And to say, so there's a couple more of these, and I'm going to recommend you don't work with star cluster figure 9-1. And so don't do that first. Use one of these other star clusters, and this is a great one to start with here. Figure 28-3. I'm sorry. So figure 28-3 right there is probably a great one to start with. And so the lab is written in the textbook for you to do this in 3 steps. Step 1, step 2, step 3, to do each one of these things. I'm going to say just go through it once and determine all of these things for each cluster the first time through, and then move on to the next cluster. And don't start with the first cluster, 28-1. Start with one of these other clusters like 28-3. And what you're going to be doing is you have a translucent overlay in your lab book. It looks something like this. And so this translucent overlay is what we call the zero-age main sequence. And the zero-age main sequence is the shape of the main sequence when the stars are first formed. And so what you want to do is you want to align the top axes. So if you look at this, you'll notice that the top axis and the bottom axis are labeled different things. You've got B minus V0 up here and B minus V down here. So this is a color index. We've talked about color index. And B minus V0 means the intrinsic color index, the color index the stars had before they were reddened. And B minus V is the color index we measure here on Earth. And so you want to align this zero-age main sequence. Your theoretical main sequence is in B minus V0, intrinsic color before reddening. And so you want to align those top axes. You'll have to slide these horizontally in order to align them. So you start here and you align this thing horizontally this way. So you'll slide this back and forth and align this so that -4 aligns with -4, 0 aligns with 0, and so on. And the first thing you can do when you do that alignment is measure how much the bottom axis is misaligned. Okay? You can see, slide it up just a little bit, and you can see that 1.2 in the bottom axis, B minus V, does not match 1.2 in the top axis. So if you read what's in the bottom axis minus what's in the top axis, you're going to have to estimate between numbers here, and you can do there's 1.2, there's 1.4, and you can even make a tick mark at 1.3 and 1.25 and so on, and estimate those values. You want to take B minus V when you have this alignment made. B minus V minus B minus V naught, the intrinsic B minus V, is going to be your reddening. That's going to be your color excess. Okay? So you got color excess there, and so that's the color excess that you've measured for that cluster. The next thing you want to do is once you have the horizontal axes aligned in B minus V0, like we had here, boom, boom, okay? So we got these things aligned. Once you have these things aligned, then you want to slide this vertically, keeping the horizontal B minus V0 axes aligned. Slide this vertically until you get a pretty good match with the main sequence right there. And so I've slid this up and down until I get a decent match along here. You see how that shape matches? Most of the stars, I might even slide it up a little bit. You want most of the stars? I don't know. I like right where it is there. Most of the stars are going to be either right on the main sequence or just above the main sequence. So stars move, low mass stars in particular down here, fainter stars drop onto the main sequence this way. So some of these stars may not yet be on the main sequence, but you see how the main sequence wraps around. Now there can be some stars over here on this side of the zero age main sequence just because of noise and other issues going on right there. The way we have to measure, measurement's not perfect, right? And so you have to decide, maybe you like that a little bit better. I don't know, that's actually not bad right there. Maybe you like that. Somewhere in there you see you get this good match to the main sequence. Once you've done that, then you measure the horizontal, the vertical axes. You see how 10 aligns with 4, roughly speaking. You want to do better than that. You want to get it down to at least a 0.1. 8 aligns with 2, 6 aligns with 0. So this, again, the bottom minus the top, the measured minus the zero age is 12 minus 6 is 6, 10 minus 4 is 6, 8 minus 2 is 6. So these axes are misaligned by 6. So the apparent magnitude is what you're measuring down here. The apparent magnitude is 6 bigger than the absolute magnitude. So then you get the distance. You just go in here and you say, I know how to do this. D is equal to 10 to the m minus m plus 5 over 5. We've done that in class. You've done it in homework. You're ready to do that. In this lab, that little m is capital V. Okay, so that's what you're reading off. In the case we just looked at it, it's approximately 6. Try to get at least another digit out of that. Okay, and that's going to give you the distance in parsecs to each cluster. So you should, as you be going through here, you should be making a table. Make a table with the name of each cluster, the color excess that you've measured, the distance that you've measured, and the what we're going to do here, the age that you've measured for each cluster. So you get the distance this way, and you get the reddening this way, the color excess this way, and start filling it out. And with the name of the cluster, just read the name that's given to you in the corner of the box right here, in that corner right here. It says NGC 752, Melot 20. For example. So these in the lower left corner of each of these clusters, it tells you the name of the cluster, and that's what you want to be reporting over here. So you're making this table to give me to turn in at the end of the lab as you go through all of that. The last step is the age. So once you've aligned, you keep the main sequence aligned, and you move this thing up and down. And as you move this thing up and down, and you've got the horizontal axes have to be aligned, so the horizontal axes are aligned, and then you slide it up and down so you get a good match to the main sequence. And you see how as you move up this direction, you form a sort of Y shape right there. You get a vertex right there. I don't know if you can see that vertex right there where you start to leave the data from the cluster starts to leave the zero age main sequence to the right. It starts to curl off. And so there you have to make an estimate to say, oh, here's my zero age main sequence and my data looks like this. The Y of that vertex right there, you want to measure B minus V0. And that's called the turnoff point, where the data starts to walk away from the zero age main sequence. So you need to record the B minus V0. Let's record that in our table. The B minus V0 of the turnoff. Okay? And then once you get the B minus V0 of the turnoff, then you can go look up the age. and you just go look up the age, we could develop a theoretical equation like this to do this, but we won't do that part. Well, we do want to use the equation for the distance, but you can just look up the age off of a diagram that we have in your lab book here. So if you go back and you look at page 233, and the cluster age here there's a graph of cluster age as a function of b minus v0 of the turnoff. So to do this, you find the b minus v0 of the turnoff. Suppose it was 0.2. Then I take my ruler and I slide up here to where 0.2 meets this curve, and I take my ruler and I read it off of here. This is a logarithmic scale, and on a logarithmic scale, you read the little number that's up here times the big number that's down here. So that would be 1.5 times 10 to the 8th years, 2 times 10 to the 8th years, 3 times 10 to the 8th, 4 times 10 to the 8th, 5 times 10 to the 8th, and so on. So then please give me the age of the cluster that you've read off there, and do that for all 9 clusters that you have HR diagrams for. When you're done with that, you turn in the table that you've got right there, and then I'd also like you to do a graph of color excess versus distance. So what color excess, this reddening that you got as a function of distance, table 28.1 tells you the distances to this, to each of these clusters. So in fact, let's not make it as a function of distance. Here's what I'd like. Here's a graph I'd like for you to make. And you can use graph paper out of your lab book. You can use graph paper off the Katie site, whatever you want to use, whatever graph paper you want to use. But here's what I'd like the graph to look like. I'd like graph to be color excess down here on the horizontal axis. What color excess did you measure? And on the vertical axis, I would like the distance you measured divided by the actual distance to the cluster. So we've got this actual distance to the cluster right here, and I would like you to look at the actual distance, take your distance that you measured, you determined, divided by actual distance. So if you got it right, that number is going to be 1. If you were 20% too high, you got a distance that was 20% too high, then that number is going to be 1.2, and so on. And I'd like to see what this graph looks like. Okay, for each of the clusters, each of the 9 points, make that graph of distance, ratio of distance measured to the accepted distance as a function of color excess. So that's what you're doing here. You're running through all of this. You're making me that table. You're making me that graph. And then as a write-up, let's not do any of the discussion questions at the back, but I'd like you to incorporate them into a discussion. So I'd like you to write a page or two summary of the work. And so in that summary of the work, what I would like you to talk to me about is each of these steps through here. So what did you find out? So tell me about the age ranges. Tell me about what issues you had with the ages, trying to determine the age. How hard was it? What you think your uncertainty was in determining the turnoff point, and then turning it into something you read from the graph. So how uncertain are you? Could you be off by a factor of 2 in the age? Could you be off by the factor of 3 in the age? Are you closer than that? What do you think about that? Tell me about the age ranges. What's the youngest cluster you got? What's the oldest cluster you got? And then talk to me about what might set the limits on those ages. Why do you think that is the age range? Are there certain ages that are more common than other ages, or are they kind of uniformly distributed through the distribution of ages that you measured? What do you know about those ages, and what is it telling you? So that's the first paragraph you write. Then you write me one about distance, and you say, okay, how did you do about measuring distances? Was that, what do you think your uncertainty is there? Remember, you're taking 10 to the power of something in distances. So if your v minus m is off by a little bit, then that causes you to be off in distance by quite a bit. So tell me the range of distances that you measured. What was the closest? What was the furthest? Are they uniformly distributed in that distance? What does that tell you about the size of the galaxy, if anything, yet? What are you seeing in the distances to these open star clusters? And so I want you to discuss the distances that you measured there. And then in reddening, do the same thing. Talk to me about the different reddening that you measured, the different color excesses that you measured, and then walk me through that graph up there. What have you learned from that graph? What do you know about the different color excesses and the different that graph? What is it telling you about the stars? What is it telling you about the galaxy? What can we learn from this work that we did? So write me sort of 3-paragraph summary of each of these things, and in that you should be able to, more or less, you're going through these discussion questions at the end. So 1 through 4, you're going through all of those sort of in paragraph form. 2, it says, in this exercise you were given B minus V0, the intrinsic color. You should include that in here. It says, how the heck do we determine the intrinsic color of the star? If we're not we're measuring the color, yet we have to know the intrinsic color. How do we determine the intrinsic color? What have we learned about in class that's going to tell us how we determine the intrinsic? That should be part of your discussion, to say, we have B minus V0. That was given to us, and it was probably determined this way. Or here are some ways it might have been determined, and so on. So this is good stuff. Work through it. If you want to, if you don't want to use your translucent overlay out of your book, you can try to come up with something like this that's going to work for you to bring it to class. If you don't want to use the graph paper out of your book, you can print some graph paper out, but be ready to go with this to do exercise 28 this week in class. And the other exercise we're going to do is 29. Our introduction to that will be just a little bit shorter, and we'll get to that in a moment. Hope everybody's having a good weekend. Thanks.